AP Chemistry, and welcome to IMFs. So a lot of this, kind of like the last unit, a lot of this is a review. Some of it just goes more in depth. You can review the stuff from last year if you find that would be helpful, or you just need you would like a stepping stone, right? But other than that, this book does have everything you need in there. It is very thorough on these units. And like it says at the top of the outline, this unit in and of itself is a whole boatload of points on the AP exam. For pretty much every qualitative answer on the free response section, something from this chapter is going to be the foundation of that answer. So it is crucial that you understand this unit. Can't emphasize that enough. All right, and do be mindful there are only a couple of lectures, a few lectures, where a lot of this stuff that goes over new stuff or things that I think are kind of hard. And there's a whole chunk in the middle that is one, direct review from last year, and two, just a little bit of memorization about states and some definitions that I don't cover via lecture because that you can just read and take good notes on. All right, so anyway, IMFs, intermolecular forces, and like the word says, right, intermolecular, right? You guys all have enough English training, right, courtesy of all those, that vocabulary stuff you guys do in English, right? Inter means between, right? So always, always, always. This is the force of attraction between molecules, right? Which is very important, right? Because it differentiates it from the forces that hold the atoms together that make up a molecule, right? So anyway, your book goes into, this figure is important, right? Just because that if we are talking about 25 degrees Celsius, being our standard, right, if something is a solid versus something else is a liquid versus something else is a gas, right, the thing that is a solid, where again, right, if we're talking microscopically, what does it mean to be a solid? My particles are closer together, right? That's what solid means, right? So if we're looking, right, anytime we're asked to sort of differentiate states based on a microscopic point of view, that's what it is, right? Solids, closely packed. Gases so far apart that the volume of the particles is negligible compared to the space between them, right? And liquids would be somewhere in between, right? Where they are still closely packed and feel a lot of relatively a lot of force of attraction. Okay, so anyway, so if we're comparing several things at the same temperature, the thing that is more compact in terms of microscopic arrangement, stronger force of attraction, okay? And that's, so state gives us one of those points of reference, right, if we're comparing at the same temperature. Otherwise, right, things like melting point and boiling point being the bigger one, right? So boiling point, always very important, right, because obviously the higher the boiling point, right, so the more energy it takes to turn it into a gas, the more energy it takes to separate one particle from another, in other words, break the IMFs, right, the stronger the attraction. Okay, just a further reinforcing of inter versus intra, right? So obviously the bond that holds the atoms together, right, that is your covalent bond, that is your intramolecular force. Intra forces are always going to be stronger, yes? Does that make sense? Like when we talk about melting or boiling, right, or solubility or filtration, right, we are never... Okay, asterisk for ionic compounds there, right? But we are never breaking an intramolecular force, right? The amount of energy available is only enough to overcome this, right? The intermolecular force, that which holds one molecule to its neighboring molecule, right? Where intermolecular forces are like, so what holds a bulk sample of matter together? So down here, they differentiate, your book differentiates inter or intramolecular forces with the term chemical bonds, right, and intermolecular forces here. And later on in the unit, it does get more thorough about metallic bonding, ionic bonding, and covalent network compounds, which would be these. All right, next up. Types of intermolecular forces. The weakest would be London dispersion forces. And note that weakest is a relative term, right, as in the concept of an LDF, right, which would be an instantaneous dipole due to an instantaneous uneven distribution of electrons, right? An LDF is the weakest force of attraction. But if we have a boatload of electrons in a relatively large sample, and at any given point in time, right, they are unevenly distributed, right, and then it induces that dipole, instantaneous dipole on its neighbor, right? Once we start to get a lot of electrons, the force becomes very significant, right? So that's not to say, right, and here is where it's very important. Our observations, right, are always going to help guide our answer, right? Because we could very well have a nonpolar substance, right, with a higher boiling point than something that's polar, right? And then if we were to think about that, well, we would say that, yeah, LDFs are the weakest force of attraction, but if we have a large molecule with a lot of electrons, therefore it is highly, keyword, polarizable, then yeah, it can have a very high melting point or boiling point. Yes, does that make sense, right? So yes, weakest, but not necessarily going to have a lower melting point or boiling point, right? We have to look at the whole substance, right? More electrons, more polarizable electron cloud, if we're going to be thorough, right? Which means stronger London dispersion force, okay? And it is an instantaneous dipole on one atom, which then induces a dipole in its neighbor, right? Which then induces a dipole in its neighbor, right? And it sort of flows through the entire sample, okay? A couple other things to think about. So one, total number of electrons, right? And so please, on your free responses, don't ever write molar mass increases, therefore stronger LDF, right? Because that's not really what it is, right? Molar mass increases, which tracks with more electrons, right? That's what we're always looking at. And it's more total electrons, okay? So this is, gotta make sure you memorize it right? It's more total electrons, means it's more polarizable, right? So anyway, another thing to consider would be surface area, right? So the more surface area where one molecule can sort of be in contact with another also leads to stronger LDFs, right? And so that's kind of like how we go back to Lewis structures, right? How first we follow the octet rule and then we have layers of stuff that we consider, right? So for LDFs, first we're going to look at total number of electrons, and then after that we're going to look at the overall three-dimensional shape if we need something else to look at, right? And so larger surface area, which enhances intermolecular contact, right, is going to be a feature. Note that LDFs are an intermolecular force, right, like noted here, right, but it can be a force of attraction between atoms for which there is no other force of attraction, like the noble gases, for example, okay? Dipole forces. So obviously this is a permanent dipole, right? So it is a molecule that has a permanent polarity, right? Again, flashing back to the last unit, in order to be permanently polar, it has to, one, right, have polar bonds, two, the atoms are asymmetrically distributed about the central atom, right, and or, right, the polarity of the bonds are asymmetrically distributed about the central atom. Going back to that, I think it was CH3Cl example, that might have been it, where this is tetrahedral, right, which means the atoms are symmetrical, but there is one bond that is far more polar than the rest of them. So obviously, you have to know your Lewis structures and your Vesper theory, so that way you can look at a shape and decide how polar the shape is, right? So here, this figure is nice because it says increasing polarity, right? So this one being our most polar. And that's always going to boil down to, right, thinking about a bar magnet, right? The more separate we can get our positive and negative ends, right, the more polar that molecule is, right? So here we have a hydrocarbon, right, which is essentially nonpolar, right? Here we have dimethyl ether, which it's hard to tell here, but what that is we have an oxygen here, and we have a CH3 group here, and we have a CH3 group here, right? Which means that this oxygen here is tetrahedral, right? Which is why we end up with something that is essentially like the shape of water, right? Just that these groups are so much more bulky that it makes the oxygen harder to separate, right? The harder to be a separate end because these methane groups, these methyl groups are so big, okay? We also have our acetaldehyde, right? Where again, we have a methyl group down here, we have a carbon here, and we have another hydrogen here, right? And so if we look at this, right, again, here, if we look around this atom, we're looking at something that is trigonal planar, right? So trigonal planar means that this oxygen is slightly removed, which means that we get an increase in our polarity, right, if we look at those dibis there, right? And for the acetonitrile, I think it's pretty clear to see, right, this is our nitrogen atom, right? Carbon, carbon, CH3, right? That nitrogen is its own separate end, so this molecule literally looks like a bar magnet, where the most negative end is isolated from the more positive end, right? Like you see here, which means that it can align better. Yes, one neighbor to the next. Good? All right. Hydrogen bonding, which really just is a very, very extreme form of dipole-dipole force, right? So when we think about it, right, so London dispersion forces are an instantaneous dipole, right? Dipole-dipoles are permanent polarity, right? Or permanent polarity, right? Hydrogen bonding just means it is so very polar, it gets its own special classification, right? And note that it is a hydrogen that must be bonded to an FO or N, right? FO or N. And it is subsequently attracted to lone pairs on neighboring FO or Ns, right? Please commit that whole thing to memory and make sure every time you're asked to evaluate if something participates in hydrogen bonding, say that whole definition to yourself and make sure it meets the criteria, okay? Now, kind of like here, these last couple examples, right, do be mindful, right, that going back to the fact that we can dissolve one thing in another, we can hydrogen bond between two things that are not the same, right? It just has to meet the criteria. We have to have a hydrogen bonded to an FO or N, which is subsequently attracted to lone pairs on a neighboring FO or N, right? So this meets all those criteria right here, right? Likewise, this also meets all those criteria because it's the same thing backwards, right? So be mindful about that. Very important, right? Especially in large biological molecules, that can happen because if you think back, right, way back to 9th grade, right? If you think about long proteins, for example, long proteins composed of amino acids, which have all those different side chains on them, right? If we think about that very long string, which then folds elaborately on top of itself into a three-dimensional structure, right? That three-dimensional structure is held together by, often, hydrogen bonding, or sometimes LDFs and dipole-dipole forces, right? That occur between side chains, right? That happen to be in proximity to one another, right? That's also how like enzyme substrate binding occurs, right? So anyway, just life things you should know. This chart here is important because it gets to, and again, they've used molecular weight here, but again, don't forget that molecular weight ties to total number of electrons, which then ties to polarizability, right? Where the point is to show that without any hydrogen bonding involved, right, yes, more electrons, more polarizable, stronger force of attraction, illustrated by increased boiling point, right? Which is the trend for here, right? And then we get our exceptions over here, wherein when we have hydrogen bonding as a possibility, the boiling point is anomalously high compared to its neighbors, right, which actually have higher total numbers of electrons, right? And note that water is exceptional even among that bunch, right? Because water is like the perfect example of hydrogen bonding, wherein there are two hydrogens and two locations for hydrogen bonding on every water, which means that every hydrogen bond is utilized. Yes, does that make sense? Whereas in ammonia or even in HF, right, that's not the case. Yeah? Okay. Ion dipole, you will only ever discuss ion dipole as a force of attraction when we are dissolving ionic compounds in water, okay? You will only discuss ion dipole as a force of attraction if we are dissolving something in water. And this flashes back to chapter 4. We saw almost the exact same diagram in chapter 4, where water, because it's polar, will orient itself accordingly around ions, right, forming these little hydration shells, right, which is then how, right, dissolving occurs. Yeah? Thank you for listening. Be good and stay tuned for more about why IMFs matter in the context of solution formation. Thanks for listening. Be good, and I'll see you soon. Bye.